What's up, Warriors? In this video, we're going to talk about the six-pack. Okay. So, what's the six-pack anyway? Well, you remember our point where we left off about economic order quantity, where the assumptions of many, but we have two that have to be present for us to use EOQ. One is that demand needs to be constant. And two is that lead time. Well, with the six-pack, we get into the other possibilities where one of these is not constant. So, in other words, if we have demand and we have lead time, we have a couple different combinations that could exist. We could have first a situation where demand is variable and lead time is constant. Or we could have the opposite, where demand is constant and lead time is variable. And we could have what I call just kind of ultimate chaos, with both of these are variable. And so I guess the analogy is that you've got, it looks like a six-pack, but really it's kind of a three-pack when you think about it, because these go hand in hand, and these go hand in hand, and these go hand in hand. Okay, so you have situation one, you have situation two, you have situation three. I just like it because it looks like a six-pack, and plus it gives me an excuse to talk about the immortal song by Black Flag with lead singer Henry Rollins, Six-Pack. Yeah, anyway, a little too excited there. Now you might be thinking, well, wait a minute. What about if both of these were constant? Well, that's where we have been. This is EOQ land. Okay, so this, on the other side of my black line, is a different world. This is the perfect world. And over here, if we cross over, this is a little bit more of the chaotic world. And the reason it's chaotic is because we have a lot more uncertainty over here. Okay, so again, the six-pack, we could have demand variable, lead time constant. We could have the opposite. We could have constant demand, but variable lead time, and we could have both variable. All right, so let's understand what's going on with probabilistic either demand or lead time. First, let's review where we were with EOQ. We know that if this axis is time, that we begin things with Q or EOQ up here, and then we encounter demand depleting at a constant rate. And at some point we hit that EOQ line or level that signals us to reorder. And when we do, we order Q. Well, in the meantime, we continue to deplete demand at a constant rate, and then the same time that we hit zero in terms of an inventory level, our replenishment comes in and brings us back up to Q. And same thing begins again and again. And we know that this area here, once we hit that reorder point, is indeed where we reorder Q. And this area here is the artist formerly known as the number of days or T actually, that passes in between, the time that passes in between orders. Okay, super. Great review of EOQ. Well, let's talk about what's going on with probabilistic demand, okay, or lead time, or both. Instead of this line here, okay, we instead sometimes encounter a line that comes down faster. Okay, so the problem is we run out before our shipment comes in. And we go down essentially in here. I call this bust in the basement. Okay, and what's happening here is that we have lost customers. Okay, we have what's called stockouts, which means a customer comes in looking for an item, but it's not here because we're beyond zero. So we have to back order it. In this day and age, if a customer comes in and we don't have the item, they're probably not going to come back. So there's a cost of lost business there. Okay. So what we want to do when we have probabilistic demand, sometimes we also have this out here. Okay. This isn't as bad because our shipment comes in and we have a little bit of excess, and that might be costly in terms we have to hold a little bit more, but it's probably not as bad as this right here. So what we need to do to prevent this right here is we're going to add safety stock. So we're going to add a buffer down here so that even when we go down here, we can continue to make it until the order comes in and we don't have stockouts. Okay, so as before, under EOQ, our formula for reorder point was demand times lead time. Okay, conceptually, what we're going to do when we're not under EOQ conditions and when we're under kind of 6-pack conditions is we're going to add some form of safety stock out here. So this is the basic concept behind all things 6-pack. We have specific formulas for each. But before we go into the formulas, we need to talk about statistics and probability. I know, but we still got to talk about it. So first thing we need to do is remember our friend, what I think is one of the greatest hacks of all time, the normal distribution. And we know that in the middle we have the mean, and we have certain marks with 1 standard deviation, 2 standard deviations, and 3 standard deviations in either direction. We know that this direction goes to, quote, negative infinity, or just infinity in that direction. And we know this tail goes to infinity in this direction. All right? So the importance, the significance of probability, okay, is going to be the z-score. Okay? So what we want to do is think about service levels. In the event that we have probability. And what I mean there is we want to say, okay, how often are we willing to experience stock out conditions? How often are we not willing to experience stock out conditions? So we might have an item like a pencil in the bookstore where we want to be at a 99% service level at all times. Who goes to a bookstore and there's no pencils there? That's just not good business. But there might be another item in the bookstore that we're okay with being stocked out with more than that. Let's say computer speakers. They don't sell that much, so we're okay not having them on hand 25% of the time, which means we would have a service level of 75%. Okay, so how does that go to this curve right here? Remember that the mean means on average. So when we establish a stockage level, we could say that a stockage level is 500. So on average, demand is 500 per se. But if we want to have that item on hand 99% of the time, we need to go out here and have some more stocks than just 500. And beyond this is safety stock. And remember, safety stock is that rainy day, just in case inventory that we have, just in case something bad happens, just in case the shipment doesn't come in on time, just in case demand spikes unpredictably. Real world examples of safety stock, I don't know. I don't know if I can really think of any examples of safety stock. Even before all this, you had that box of cereal underneath the sink just for that rainy day where you felt like jamming on some cereal. Or you got an extra rubber chicken just in case you... Anyway, back to this. So beyond this, we have safety stock, and how far we go this direction, okay, how many standard deviations to the right of the mean is associated with how much safety stock we want to have. So let's suppose that we want to have customer satisfaction, a service level of 99% all the time. So that would be somewhere out here. That means that if demand falls here, we're covered. If it falls here, we're covered. If it falls here, we're covered. If it falls here, we're covered. We're just not covered this little piece right here. Okay, so the trick is there's a value that we're going to figure out what that is. But to figure out what that value is, we need to know how many standard deviations it is from this value over to here. And remember, in statistics, we talk about the number of standard deviations a value is from the mean is a z-score. So let's suppose that we have a service level. We want to keep a service level of 99.73%. What would be that z-score? Well, there's two ways we can figure that out. One way is what I call the Mike TV way. Who is Mike TV, you ask? Well, if you remember Willy Wonka, Mike TV is that bratty little kid who gets shrunk down into the TV because he wants to, and he's spoiled and he's selfish and all that, and then he can't get out of there. It's a movie that caused me more PTSD than Amityville Horror, Freddy Krueger, and Jason Voorhees combined. Anyway, what we want to do is shrink down and go inside the Z table. And so when we do that, if we want a service level of 0.9973, we're going to go on the inside here because these are all probabilities. And we're going to get down and we're going to shrink down and we're going to look for 0.9973. And there it is right there, right above my cursor. Now what we need to do is figure out what z-score that corresponds to. First thing we're going to do is look left. Trace that back over here to 2.7. Next, we're going to look for that hundredths place, which is at the top of the column. So we're going to go back over here to 9973, and we're going to go up. But once we have this memorized, we're going to know that's the 0.08, and we look up here, and it is 0.08. So 2.78 is the z-score that corresponds to a 99.73 service level. So that's just an example of how to get a z-score. And we're going to need that z-score when we start working with our formulas. So it's important that you refresh on what a z-score is, i.e. the number of standard deviations that a value is. In this case, we're going to be dealing with positive z-scores that are to the right of the mean, and we're going to choose the z-score based on the probability, i.e. the service level, that we want a particular item in stock. Again, not all items have the same service level. A pencil might have a 99% service level. Some headphones, a special clock, maybe an artist pad might have something much lower. We think of an auto parts store, we might have mufflers on hand all the time. We might not have computer chips that go into the car that govern how the car functions. We might have those on 50% of the time and then just order it when it comes in. So, back to business in terms of looking at the various conditions within the six-pack. The first thing we're going to do is talk about when demand is variable and lead time is constant. And so we are going to use the formula for ROP. And you'll see a pattern here pretty quickly that we're going to take the average daily demand, little d, and we're going to multiply that times the lead time. And then we're going to bring in our friend Z. Okay, again, Z depends on that service level that we want. And then we're going to multiply that thing called by the sigma for DLT. Now, I just got to take a little side note, and this always reminds me of the McDLT that was a sandwich when I was a kid that I don't know why they discontinued it. Well, I can kind of guess why, but I like the DLT. Anyway, that's not what the DLT we're talking about. The DLT we're talking about is the standard deviation of demand, okay, times the square root of lead time. So this is that. Pretty simple. Let's do a quick example. So let's suppose that we have the average for D is 15, normally distributed. That's pretty important. Lead time is 2 and is constant at 2. Now, wherever we have an average for a variable, we should have averages just like mean, and so where we have a mean, we should have a standard deviation because all that implies variance. Hence, demand is variable, lead time is constant. So, the standard deviation of demand is 5. And we want a service level of 90%. We could rewrite that as 0.900. So we want to figure out what our ROP is going to be equal to, knowing that ROP equals average D times lead time plus the Z times the standard deviation of DLT. So, first thing we want to do is figure out what Z is going to be out of this. So we're looking for 0.900, and unfortunately that is between these two numbers. So I won't give you an example that looks like this, but you would average those two, and I think it comes out to be 1.28. We see the 1.2, and we can go up here. Or another way we can be smarter than this is we can use the function and put in 0.90, and that should return 1.28 as Z. Okay? So, either way, we're going to use Z equals 1.28. So I'm going to figure out what my ROP is. My ROP is going to be 15 times 2 plus 1.28 times that 5 times the square root of 2. And that equals 30 plus 9.02, which we could round down to 39 units. Now, important to realize, or for me to emphasize, that whenever you see a Z, so this piece right here is your safety stock. And your safety stock is a subset of the ROP now. Remember our diagram at the beginning, the modified sawtooth. So, our safety stock is 9 units. Our base stock, so to speak, is 30. Okay, so that's the first situation, or one of the 3 situations in the 6-pack where demand is variable, lead time is constant. Here's our formula. First thing we got to do is figure out what Z is. We do that by taking this service level and going into the Z table. In this case, we had to average 2 values to get the in-between value of 0.900. That gives us a Z value of 0.128, or we could use the Excel function norm.s.inverse to get that as well by entering that here. Once we get that Z, we've got everything we need. We plug it into our handy-dandy formula, and we just need to keep straight church and state. Everything past the Z is safety stock. Everything prior to it is what we call base stock. Let's go on to the next problem, or next situation of the 6-pack. Flip it. Not like Missy Elliott, lay it down, flip it and reverse it, although that does come to mind, where we have lead time that is variable and demand that is constant. And here we're going to use a formula, ROP equals D times the average lead time. Notice that trend. So we begin with a product under the other situation where demand was variable. We had the average D times lead time. Here it's reversed because demand time is variable. So that's a little bit of a commonality between those two situations. And then we're going to have our plus, and you know what's coming, our friend the Z. And where Z is, we need to have some standard deviation involved. So this gets kind of interesting. It's a little bit different. We have D kind of stuck in here. And then, so that's a times. We have Z times D, which I always felt was interesting. And then we have the standard deviation of lead time. Okay? So, let's do a problem, an example of that. Let's say we've got a situation where D is constant at 10 days. And our average lead time is variable at 6 days with the standard deviation. And again, anytime we have an average or a mean of a variable, we should be reaching for that standard deviation. We know it's coming, we should be looking for it. If something is constant, it's constant, there is no deviation, the variance or the variation is 0. So there's no need to look for standard deviation. All right, in this example, we have the standard deviation as 1. And our service level is 0.98. So first things first, we're going to use the norm S inverse with a 0.98. And that'll give us a Z-score of 2.055. So we're going to plug everything in our handy-dandy formula here. Looks like we got everything. We have D, we have average lead time, we have Z, we have D again. I should put this in black because this D right here is indeed that D over here. Funny, just kind of funny how it appears twice. And what else? We have the standard deviation for lead time is 1. So let's rock our formula. We're going to have 10 times 6 plus 2.055 times 10 times that standard deviation of 1, or that value of 1. So we'll have 60 as our base stock plus 20.55 as our safety stock. Just to reinforce things, base stock here, safety stock here, safety stock here. Anytime we see that Z, we know we're talking about the safety stock because that's taking the probability of those variables that change into account and adding that buffer underneath our basement, essentially. So we don't hit 0 and we don't have stockouts. Okay? 80.55, and whether we round up or down matters less than just kind of the process and what we're doing. Okay, so this is the second situation, or another situation in the 6-pack where we have lead time variable, demand constant. And finally, let's go to our most complicated formula where we have both lead time and demand variable. Okay, once again, that is the incredible rhyme animal. We have demand variable and we have lead time variable. Anything goes here. So we have a heck of a formula here. It starts out not looking so threatening, but then it kind of just gets nuts. Okay, so I need to start way over here. So ROP in this case is equal to, and since we have both of these variable, we're going to have a lot of stuff up front where we have average demand times average lead time. And then it looks kind of innocuous right here, Z and DLT. And so you go, the DLT again, I'm cool with that. Well, this DLT is not the same as the other DLT. So the question is, okay, what is that? Well, these we should break out separately. Too much black on the board. Standard deviation of D is the standard deviation of demand. Okay, so that works out. Standardization of lead time is the standard deviation of lead time. Okay, but in this instance, with this formula, the standard deviation of DLT is one heck of a thing, I will tell you. So here we go. It is the average lead time times the standard deviation of demand squared. A little bit of PEMDAS action going on here. Plus, let's get a different color up here. The average daily demand, D, squared, times the standard deviation of lead time squared, all under the square root. So if you have this situation going on, I mean, you just get a Snickers bar because you're going to be here for a while. So let's rock a problem. Here we have anything goes. So again, demand is variable and lead time is variable. So let's just go down the numbers. Demand is variable, normally distributed with an average of 50, just to stay consistent. Daily demand. And the standard deviation of daily demand is 16. Then we have lead time, which is variable with an average of 5 days, normally distributed, all that good stuff. And the standard deviation of lead time is 1. Service level, we want to have this item on hand 95% of the time. So if we do that, we will get 1.645. Okay. So looks like we have everything we need. We just need to go through this crazy formula, which you've probably forgotten by now. So I'm just going to write it back up again, and we'll try to hang everything underneath it. First, we have base stock average demand times average lead time. A whole bunch of stuff. Average lead time times square root of demand, or excuse me, standard deviation of demand squared, plus the average D squared times the standard deviation of lead time squared. So let's see if I have enough room. To do all this. Let's get a different color, shall we? Seems like I left a Z out somewhere. And let's see, just to make check, I sure did. So that Z is going to go in front of this bad boy right there. Z times all that. So my Z, 1.645. Okay, so I'm going to have that times, and I'm going to put all that stuff underneath the square root. Here we go. Average lead time is 5 times the standard deviation of demand squared. So that would be 16 squared plus average D squared, which is 150 squared. That's going to be a big number. Times the standard deviation of lead time squared. So thank God, that's going to be 1. And just to, sorry Kylie, beat a dead horse, everything after this is safety stock, base stock. And for this math, I am going to call out both chickens to tell me what that answer is. And the answer we get for that is $750 is the base stock. $253 is the safety stock. 1,003 units. Lot going on. So, as always, let's recap. Okay, why do we call it a 6-pack? Because when we have demand and we have lead time, we have really about 3 conditions that could exist. It kind of looks like a 6-pack when you line it up. Demand could be variable, or lead time could be variable, or they both could be variable. And here, this could be constant. That could be constant. So we have this situation, we have this situation, and we have this situation. You could argue that we have an 8-pack where this is constant and that's constant. But in my mind, this is a different world. This is an EOQ world. This is a perfect world. Over here, this is a world of uncertainty. And where we have uncertainty, we need to think about probability, which is a fancy way of saying likelihood of what will happen. And hence, we enter the Z, which tells us how many standard deviations we need to have to the right of the mean for safety stock depending on our service level and how often or less often that we want to not have a particular item on hand. So from my experience, the trick is when you're doing these problems is not so much working the problems, it's framing them. It's looking at a particular situation and saying, am I here? Am I here? Am I here? Or am I here? And part of those techniques are, if demand is variable, then I should be looking for an average demand or a mean demand, and with that, it should have a standard deviation. If demand is constant, I don't need a standard deviation because standard deviation is 0. I have no variation. And the opposite with lead time. If lead time is variable, I should be looking for a standard deviation for lead time. And if both are variable, I should have averages or means for both and standard deviations for both. So that's it. That's the beautiful 6-pack. Remember what safety stock is all about. And of course, Warrior on.